Hello, welcome back to this set of videos for electricity and magnetism. We will see today Gauss law and potentially some examples about how to use it. So the first thing we must check when we talk about Gauss law is the concept of field flux, or the flux of a field. In this case, let me clear this image. We have electric flux. I'm sorry, and the definition of the electric flux is just as you can see here in the picture. Imagine that you have a curved surface right here, and we make a grid on it. Let's take this part one of the grid. Imagine it as a window of a closed submarine. And if I open the window and these arrows represent air, air will go out of the window, and the amount of air that comes out of the window is proportional to, of course, the amount of air coming out, the size of the window, but also of the angle between the perpendicular to the window and the field itself. Now, in this case, electric field is represented with E letter as usual, and the surface A is represented by its perpendicular vector. So the definition of the flux would be given by a dot product between these two vectors, E and A. And remember that the dot product takes the magnitude of the vectors and multiplies them with the cosine of the angle between them. So if I take this surface number one, electric field is coming out from the surface. So this element of flux would be positive, while at point number three, this window air is coming into the surface, so we will take this flux as negative. Now, in the case of window number two, the vector A is perpendicular to the field, so that there is no electric field coming out of this window, so we will take this flux element as 0. So to make a summary, the electric flux in this case could be understood as the amount of field represented as these arrows that come out from a certain part of a surface. Let's work out some examples here. If we have a closed surface within which we have a positive charge, we've already discussed in the previous video that the field caused by a positive charge points away from it. So if we take surface number one, all the arrows of the electric field will point away from it, so that the flux is all coming out of the surface. Let's just remember that when the field is coming out of the window, we take the flux as being positive. So in this case, through surface S1, we will have an all positive flux. Now, if we take surface S2, which is this one a little deformed here, we will see that the same amount of arrows come out of this surface number 2, so the flux through surfaces 1 and 2 is exactly the same. And then for surface number 3, again, is a little bit larger. However, the same amount of arrows are coming out of it. So all the fluxes through surface 1, surface 2, and surface 3 are exactly of the same magnitude. Now, if we look at the picture on the right, we will see that for, again, a positive charge, electric field lines are pointing away from it, and the closed surface is here. Imagine this thing as a balloon with a weird shape, so that the field lines coming out of Q puncture the balloon, come into it, and then on the other side come out of it. So all of the surface come into the balloon, but later come out of the balloon. So whatever the signs are, the electric field comes in, but then later on come out of the balloon. So the net flux here will be 0. Gauss's law for electric field states that the flux through a surface is proportional to the charge within that surface. So we'll see that for surfaces S1, S2, and S3 on the left, they're all positive and they are all exactly equal because the charge enclosed in those surfaces is always the same. And to the right, we will see that since there is no charge enclosed in the surface, then there is no field whatsoever, or no flux, or in other words, the net flux equals 0 in this case, right? So this Gauss law will be useful for me to calculate electric field under certain symmetry conditions, right? So let's just remember here that that the flux is represented by the integral over a certain surface of the field dot product with the differential of area, and this is equal to the charge enclosed in the surface and divided by epsilon 0. Remember that epsilon 0 is permeability of free space. In Spanish is permeabilidad del vacío, and is related to K. Remember that Coulomb's constant K was equal to 1 over 4 pi epsilon 0. Now, we can use Gauss' law in order to calculate the electric field for different distributions, as I mentioned earlier. So imagine we have here a conducting material sphere, so that all the charges will be stuck at the surface. So there is no free charges inside the material. So if we use Gauss' law, we will see, this is not a conducting sphere, this is an insulating sphere, it says here insulating sphere. So the charges are uniformly distributed inside the sphere. So using the Gauss' law, we will be able to calculate how, as I go from the center to the surface of the sphere, I will have this expression, which will allow me to calculate the electric field at points inside the sphere. And once I go out of the sphere, I will see that the electric field is calculated just as if the sphere were a point charge located at the center of the sphere. For a wire that is uniformly charged, remember that this charge distribution was labeled lambda, and this was equal to the amount of charge located at a certain small portion of the wire. In this case, I use Y because the wire is vertical, and usually vertical axis is labeled with Y. Now, looking at the wire from the top, I can see that the charge is distributed like this, and the electric field lines come out from the wire. So this blue surface here is the Gaussian surface, and if I look at it from the top, I will see this dotted line here, which represents the cylinder, which is the Gaussian surface in this way, and I can work out Gaussian law, solve the integral of flux, and find out the corresponding result for a field at a certain distance r from a linearly distributed charge. The same idea can be applied later on for a surface like this. This is sort of looks like a piece of bread. Imagine that the positive charges are distributed over this surface. Imagine that it is like a jelly, and we will use a Gaussian surface in this case, this blue one, as this cylinder that goes across the surface from the backside, which we don't see, so we represent as dotted lines, and the front side, which we represent with solid color, with solid blue color. So applying Gauss law, we can also figure out the electric field due to a surface distribution. Remember, we represented it with a sigma letter, and this was equal to dq over dA. Now, in this way, we can make a summary and state that whenever we want to calculate uh, electric fields by means of Gauss law, we have to look at the symmetry of the system. In this case, uh, if we're talking about a sphere, of course, we have a spherical symmetry. Therefore, a Gaussian surface would be a sphere. In the case of the wire, there is cylindrical symmetry, so that the Gaussian surface would be a cylinder. And in the last case, we will use a coined shaped flat cylinder. So this thing, imagine that it is a very, very not flat, but not very tall, let's say, so that we have a coined shaped cylinder. So by applying these ideas, we can conclude the same electric fields as we have shown in the previous presentation. Let me show them again for you. I have here the formula sheet at the end of part 1, which is this one here. So you can see, for example, in this case here, we have a solid insulating sphere with radius r. So for the outside of the sphere, we have this expression. So the electric field of the sphere outside the sphere will be exactly the same as a point charge, whereas for the inside of the sphere, we have a linear dependence on r. Remember, small r is the variable r, and capital R is the radius of the sphere. So we can work this out in later examples. So this is the end of part 2, and I will proceed to make a third video with some examples about calculations, which will start over here, and see you in the next video.